effect.
Okay, great. Thanks to the organizers for putting on this nice conference. I'm Maria Neuzil, and as Alexei foreshadowed many times, I'm going to be talking about some similar topics as his talk. So this is based on a work in progress with she and Alexei, though this talk will be mostly self-contained until the end. Okay, so the big picture is that I'm going to be talking about physical consequences of theta terms. So this is going to include both these fancy abstract new symmetry theta angles that Alexei was talking about, but also just regular old Lagrangian theta terms. And for this talk, I will be mostly in totally familiar territory talking about Maxwell theory.
Things not going away. Weird. So. Okay, sorry about that.
Okay, no problem. Okay, so we'll start with reviewing / lightning introduction to the standard Witten effect before I start talking about some newer interpretations. So this is either something that you already know and have read in a textbook, or maybe you're not familiar with it, but I'll give you sort of a modern perspective on what people call the Witten effect. So we're going to be doing 4D Maxwell theory with a theta term, and all my equations will be for Euclidean signature. So we just have our regular U1 gauge theory, no matter, with a theta term. And the usual reaction to this is, well, okay, the theta term is a total derivative, so it's not going to affect the equations of motion. And furthermore, for a U1 gauge theory, there's no instanton configurations like on R4 or something. So you might say, okay, well, this term looks totally invisible, so why should we care about it? But it turns out that it actually does have physical consequences, and that's called the Witten effect, which one way to state the Witten effect is that theta leads to the fractionalization of electric charge. Another way that you see people state this is that magnetic monopoles become diodes with fractional electric charge. But I'm going to be introducing this from using some modern language. So I'm going to be talking about this from the perspective of Maxwell's one-form symmetries, so the electric and the magnetic one-form symmetries.
But in PEDs, there is no monopole.
So
there is no magnetic charge.
We could do like a probe if you have a probe, yeah, for example. Yeah. Okay, so first a little bit of semantics is that U1 symmetry charges are of course always integers by definition because they're just representations of U1, and yet we have this phrase that electric charge gets fractionalized. So in order to be precise about this, we just have to distinguish between what you could call a symmetry charge, and that's really these honest to God integer labels that label the representations of groups. But then there's something that you could call a physical charge. And these are the quantities that actually show up in the physics. So it could show up in the string tension or in Gauss's law, for example. So I've just written out magnetic and electric versions of Gauss's law in these variables. In this particular case, the physical magnetic charge is the same as the symmetry charge. But a short calculation will show you that the physical electric charge picks up this fractional contribution from theta. And it depends on the magnetic symmetry charge. Okay, so the standard punchline is that the Witten effect affects the physical electric charge via the magnetic charge. But you might ask if this is the only thing that happens, because in particular, can we say anything about theta without referring to the electric charge? Because you could easily cook up some situation where the electric one-form symmetry is gone, you don't have a charge to talk about, then you might want to ask, does theta still do anything at all? So for example, we could consider a case where we add some unit electrically charged matter to kill the electric symmetry. And whatever effect remains will be only in terms of the magnetic symmetry. And so it will, in some sense, be more robust because it requires fewer ingredients. So this is precisely what we're going to be defining as the topological Witten effect, the effect that depends only on the magnetic symmetry. And a little bit of foreshadowing here. So in Maxwell theory, the topological Witten effect is going to involve magnetic strings charged under the magnetic one-form symmetry. And so in particular, we're going to want to look at regimes where the magnetic symmetry is not spontaneously broken, because we want to have nice finite tension isolated magnetic strings that we can study. Okay, so one way that we can do this is we can put the theory on some compact manifold to prevent the symmetry from being spontaneously broken. And here I'm just choosing some maybe odd looking choice here, S1 times S1 times S2, but this really is just like ends up being a very convenient choice for interpreting some equations that I'm about to show you. But really the point of doing this is that we want to make sure the magnetic symmetry is not spontaneously broken. Okay, so I'll start with the claim and then kind of dissect this equation a little bit. So the topological Witten effect is that there is an isomorphism between twisted sector Hamiltonians of this theory. And we will get to the physical implications very soon, but we'll keep it abstract for just a few more slides. So to just explain my notation in this equation here, I've got h of chi, which is the Hamiltonian of the twisted sector with a magnetic twist chi. And all this means is that this is the theory in the presence of a static spatial background field for the magnetic symmetry with holonomy e to the I pi. Okay, and then this Hamiltonian with this background field turned on can further decompose into a sum over the charge sectors labeled by the magnetic symmetry charges. So at the end of the day, we have this expression with a particular background field twist, a particular magnetic charge, dependence on theta. And then the claim is that we can basically reshuffle the dependence on theta such that it is actually interpreted as a magnetic background twist. Okay. So I'll give you a few more equations to make this a bit more concrete. So what we're going to do is turn on a background magnetic field with a particular holonomy pi, so that we can study the twisted sector to see the effect of the twisted sector versus the effect of theta. And so what we can do is evaluate the partition function, and here I've written down basically the most interesting part of the partition function. And how we should read this equation is it's a sum over string excitations, and then it depends on the energy of those string excitations. So very specifically, the sum is over the electric and magnetic symmetry charges, if the integers, for those string excitations. You then get some geometry factors. But then the interesting thing here is that theta and the magnetic twist appear in basically the same way in this expression. And you can see that you could easily just redefine pi to absorb the effect of theta here. Another thing to note is that, again, we're still in Maxwell theory here. We still have the regular charge fractionalization Witten effect. So we also see that in this expression. Here, the electric charge picks up a fractional contribution. And if you, again, compare to the interpretation of this partition function, this is saying that the string tension is affected by this physical electric charge that has gotten fractionalized. But this is just sort of an added bonus for Maxwell theory because we have extra symmetries, and in fact, it depends on the anomaly between the electric and the magnetic symmetry.
But pi is not about like theta doesn't cancel. Okay.
So we've turned on theta at the beginning, and then chi we've turned on a background field.
Right, but you cannot write it as additional theta, say in the background. I wonder if it was a piece of theta.
So basically, the interpretation is back. So at the end of the day, I want to make a claim about the Hamiltonians.
Yeah.
And we can basically read off those Hamiltonians from this expression. And then you can redefine your Hamiltonian to have a certain twist where the twist is absorbing theta. Yeah. Okay. Okay, so to summarize the old and new perspective of the Witten effect, Maxwell theta has two effects. One is it fractionalizes physical electric charge by the magnetic charge. And then the other is that it activates effective background fields for the U1 magnetic symmetry, i.e. it turns on a twist. But because there's these two different seeming effects, it motivates fine-graining the definition of the Witten effect. So the thing that we're focusing on this talk is what we're calling the topological Witten effect, and that's this phenomenon that theta activates a background field slash a twist for this magnetic symmetry. And all you needed for that was just the magnetic symmetry to discuss the charges and the twists. Then what I'm now calling the charge Witten effect, or what you could say is the Witten effect, the standard Witten effect, that's this usual understanding that theta leads to charge fractionalization. But for that, you need two symmetries and they need a mixed anomaly in order to see that additional effect. So the interesting thing is that you could have the topological Witten effect, but not necessarily have the charge Witten effect. Just depends on if you have these other ingredients. And in fact, I'll show you an example right now where you have the topological Witten effect, but no charge Witten effect. And this example is going to be the Higgs phase of the charge 1 abelian Higgs model with a theta term. So it's just the usual Maxwell action. The theta is coming from Maxwell, and then we have this unit charge scalar that's going to condense. So a few comments. The electric symmetry is completely destroyed because of this electrically charged matter. So it doesn't make sense to fractalize electric charge because it's ill-defined in the first place. So there's no way that we can talk about the charge fractionalization Witten effect in this theory. But nicely, the magnetic symmetry is still there, is intact. It is not spontaneously broken, which means that we have magnetic confinement. So there are nice magnetic string excitations with finite tension that we can study, and the physical effects will be in terms of these string excitations. Okay, so the claim was that the topological Witten effect implies theta is equivalent to turning on a magnetic twist. And the fact that you may know very well or may not have been familiar with is that different twisted sectors of a theory have different genuine versus non-genuine operators. And what this language means is that a genuine operator is just an operator that's well-defined on its own, full stop. Whereas a non-genuine operator needs to be attached to something topological in order to be well-defined. So this just depends on the dimensions involved, but it could be a point operator getting attached to a topological line. It could be a line operator getting attached to a topological surface, just depends on the example in question. But the takeaway is that different twisted sectors, you need to attach different things to your operators to make them well-defined. And the particular relationship between theta and the U1M twists implies that theta is going to attach topological surface operators to the magnetically charged Tooft loops. So very schematically, you can see this by just evaluating some correlation function of a nice Tooft loop with magnetic charge M in the presence of theta. And what you're going to do is just take the theta dependence in the partition function and evaluate it, remove the theta dependence from the partition function, and then you just end up with the insertion of some other operator. So you take theta out of the partition function, so now you're in a theory with no theta at the expense of introducing this new operator that has theta dependence. And if you look at this operator for a second, you'll notice that this operator is precisely the generator of the one-form magnetic symmetry, the surface operator. So the interpretation is you can trade theta for attaching a topological surface to your Tooft loop. And the physical consequence of this is that the topological Witten effect induces Harnaff-Bohm scattering effects for magnetic strings. So to discuss these Harnaff-Bohm phases that I just alluded to, we need to think about the geometry a little bit. So if you think about the usual textbook Harnaff-Bohm example from quantum mechanics, you can interpret the solenoid as some like fixed probe operator that you just put in your theory once and for all, and then you consider the particle excitation and the path that that excitation takes around the probe. So on the one hand, you're considering a probe that's fixed, non-dynamical, and then on the other hand, you're considering the dynamical excitation that circles around it. So we're going to do the same sort of thing here, but the dimensions are just different. So the fixed probe in this case is going to be a Tooft loop, and I'm just drawing a 3D time slice. So the Tooft loop is going to be extending in the time direction. I'm just getting this these 2 points where it intersects the XY space. And then what we're going to do is look at the path of a magnetic string excitation that links with this Tooft loop in 4 dimensions. So this is going to trace out a 2-dimensional torus, basically, as I've drawn it here. So I start with the theory with theta turned on. This magnetic string does this, follows this path. And then how we're going to, oh, was there a question? Yeah.
Maybe I missed something, but can you understand this from this fact that you get it just side like comparable to the effective three-dimensional reduced to photon giving all? You take 2 magnetic units and also strength.
Yeah. So right. So I will have a comment about interpreting this in terms of the world sheet of 2 magnetic strings. shortly. So it's, it's.
It looks like it's sounded very good. Especially in children. But these training rules, we don't.
Yeah, so when the world sheets of the two string excitations intersect, they'll pick up this.
Also, not like when you take long straight strings around it.
I haven't thought about that geometry yet. Yeah. Yeah, so. Okay. You? Okay, so let's just evaluate this particular configuration. So again, the strategy is that we start with a theory with theta turned on, and then we are going to evaluate, we're gonna trade theta for this surface. So again, we just trade theta at the cost of filling in this surface operator, filling in the tilt loop. And again, when you just take that 3D time slice, that's just gonna be filling in this line. Okay. And so what's gonna happen is, once this magnetic string crosses and intersects this symmetry generator, it's going to pick up a phase for the usual reason that these symmetry generators act on charged objects. So the magnetic symmetry generator acts on the charged magnetic string and you get a phase. And this is precisely the Aharonov-Bohm phase for magnetic strings. And this is the comment that I was alluding to, which is that you can also interpret this as an interference phase when the world sheets of two magnetic string excitations intersect. And that's precisely because this tilt loop itself generates magnetic string excitation. So it just depends on if you're considering the operators versus the excitations, and then you just have to take into account the appropriate dimensions. Okay. So to summarize all of that discussion of the Witten effect, sort of old and new, is that the topological Witten effect has an interpretation in terms of Hamiltonians, which is that you shuffle the twisted sector Hamiltonians with a given charge. So this is redefining some background field to absorb theta. And then the second perspective that I gave to you, which is related, is the operator perspective, which is that you attach symmetry surfaces to these magnetically charged tilt loops. And we saw that the physical consequence was Aharonov-Bohm phases for magnetic strings. So this has all been in Maxwell or Abelian-Higgs, but you might want to know how general all of this is. And in fact, this is where Alexi's talk starts to come in. So to see the topological Witten effect, as I've just described it, all we really need to refer to was the one global symmetry of the theory, the U1 magnetic symmetry. And we talked about the charges, we talked about the operators, the twists, all with respect to that symmetry. But from Alexi's talk, we saw that you can use a global symmetry to construct abstract symmetry theta angles. So in fact, the topological Witten effect, as I've just described it to you, follows precisely from the symmetry theta angle construction of the last talk. So I'm going to be pretty schematic about this, but just try to give you a flavor for what's going on. So again, remember the topological Witten effect shuffles these Hamiltonians, changes the twist at the expense of absorbing theta. So what I'm going to do is now consider some other theory, call it Z, and for simplicity, I'm just going to say it has some discrete global symmetry. Now I can write down a table of all of these subsector Hamiltonians labeled by the charge under the symmetry G and also labeled by whatever twist I turn on for that symmetry G. Let me just fill out this table. And the topological Witten effect is going to mess with the twists while preserving the charge. So as you can see here, the charge label does not change as you do this redefinition. So in terms of this table, what's going to happen is the columns are going to be shuffled like within themselves, vertical shuffle. Okay, so in the Maxwell case, there was a particular prescription for how you do this shuffling based on theta and the magnetic charge. But in general, if you come up with some other way to shuffle this table, you would also call that a topological Witten effect. However, randomly permuting the entries in this table around is pretty disastrous. You're most likely going to end up with some inconsistent QFT that violates locality, and it's just bad. So you need to come up with some way to shuffle these columns such that you're preserving locality and keeping everything under control. And it turns out that the legal shuffles of these tables is precisely the STS construction of the previous top. So just at the level of pictures, I'll tell you how these entries are shuffled. So the punchline is the STS procedure as a whole shuffles entries within each column, which is going to produce a topological width effect. So basically what you do is step by step do these operations, S, T, and S. And each one of these on their own is known to be a nice locality preserving operation. So in all, you'll get a nice locality preserving operation. So without going into too much detail, first you gauge the global symmetry of your original theory. And this has the effect of basically swapping the twists and the charges. So I have transposed the table, and now you have a new theory in terms of some dual symmetry with the table like so. And then you can show that if you stack an invertible theory at this stage, that's going to be a horizontal shuffle of these rows. And then you simply gauge back, transpose the table back, and the net result is that you horizontally shuffle the columns once you did this composite procedure. And so this manipulation is what you need to show that, you know, operators will get attached to surfaces, you get a Harnack bone phases, and so on and so on. Yeah.
So STS gives a legal shuffle, as you said.
Yes, yes.
Have you shown the opposite, that
But all legal shuffles are STS.
STS for the
Yeah, so I think it comes from the fact of how many options you have for these invertible theories that you can, like the invertible, stacking the invertible theories produces all the legal horizontal shuffles.
It seems like
Yeah.
there should be a whole SL2Z multiplet of these transformations, not just S and T, but everything they generate, strings of S and Ts. And you're only getting a very small subset of those from STS. So you could do STS, then you could do T without doing
Yeah,
STS,
yeah.
then you could do another STS. That would be different than a single STS.
Yeah, so, well, depending on what you do, like, if you just do T here, it just doesn't have the same interpretation because you're stacking with this theory, but the final result is
Through the plane T at an intermediate stage.
at an intermediate
between
stage.
two STSs. And I think you'll get something different.
It may, I'm not sure, but it may be possible to reduce them to a simpler one.
So.
Okay, not sure, yeah.
Yeah, just on.
Yes.
In general, this does not form of SL2C group or something like that. Generally, it does not.
In general, it does not.
Yeah, because the something already.
Okay, yeah. So G, because G hat and G are not.
Yeah, because they are region. Only some special cases, they can use it, and in that case, it's have this kind of SL groups structure, but in general, you don't.
Well, that brings me to the end of my talk. So the conclusion here is that the standard charge fractionalization Witten effect is just a special case of a more general effect, which we're calling the topological Witten effect. And abstractly, we saw that the topological Witten effect shuffles twisted sector Hamiltonians within fixed charge subsectors. And then physically, we saw that this means, in the case of Maxwell or abelian pegs, that strings get attached to surfaces and cause these magnetic strings to pick up the Harnack bone bases. And then the final comment is that the topological Witten effects are consequences of this abstract symmetry theta angle construction from global symmetries. And with that, I can take more questions.
For the last year,
Yes. Yes, exactly.
And there's, we find some new.
I don't think we have a new one yet, but we show that it works for like massless relays. Or under it.
I run, let's say, it doesn't work the standard model, standard model, you have this superficial level, we have genetically have two theta angle, one is, the UCT and another one, the right?
Yep.
So, or also do as a do equals one. So, And then there's this general consideration of course, but and is that electroweak angle, it does not, physics doesn't depend on the electroweak angle, so there is only one that angle at this level, okay? When you explain about this kind of, external flow, whatever, I follow what you said, but then, back then in UCD, the question was whether measurable quantity, like, say, magnetic moment of Newton depends on that element. Now, okay, now we are saying, doesn't mean that, say, observable quantity like magnetic, this electric moment of Newton would depend on this additional parameter.
So, you're talking about the extra theta angle that Alexei was introducing, or interpreting the regular Yang-Mills theta angle from this perspective?
Besides this distance, there's two actual angles.
Yeah.
One is associated with this electroweak field, and another associated with field. Right? So I don't put an additional coupler.
Yeah.
Whatever. Yeah, but still looks like, because when you say that in principle this electroweak angle also would be acting in the manner you described.
Mhm. So as far as the Yang-Mills theta angle is concerned, so it's not, the discussion that we've had here doesn't affect like local observables, like the magnetic moment of the neutron, for example. So it's all about these like excited states.
What means local observable? Electric moment of neutron is what means local observable. It is just physical characteristics.
Mhm, mhm.
You see, it's not.
Yeah, So this
Question is whether it can contribute to dynamics of the theory in such a way that it could show up and then
Mhm.
end in itself.
Yeah, I'm not, I don't think so. Yeah, I don't think so.
Okay, there are no more questions.
That's fine.